Hey there, corn children. Today we are going to be enjoying finding all the points of inflection of a function. All right, justifying our answer as we go. Let's be clear. Point of inflection is where the function changes concavity. It is a point that is defined on the function, and we will need to justify this point of inflection by showing a change in concavity. Well, it does need to be a point on the function, so the first thing we need to realize is that this function is well defined everywhere. It's a continuous function. If we had a vertical asymptote, we would want to include that in our interval of analysis because a function can change concavity right and left of an asymptote or any point of inflection. But this one, it's good to go everywhere. We have a nice pretty polynomial, so we're going to dive right into finding the second derivative. It's the second derivative that tells us about concavity. So let's take the first derivative. This is a pretty nice function, pretty simple to do derivatives on. There's your first derivative. I'm going to plow right on through into the second derivative. And this is a nice, well-behaved linear function, so the analysis is going to be pretty easy. You'll notice I did factor it. Factoring it will make our lives easier in most cases. So now, the second derivative is going to tell me about the concavity of the original function. It's the second derivative that we're going to analyze to get points of inflection. So I need to know, when is the second derivative 0 or undefined? It's never undefined, so I don't have to worry about that, but I do want to know, when is the second derivative equal to 0? So, simple enough. We set this equal to 0, and we get a happy answer of x is 3. You have in no way justified anything at this point in time. The second derivative equaling 0 gives us only potential points of inflection. This is not a justified point of inflection at this point. We don't know if the second derivative changed sign. So we are going to show that by making a table. I'm going to slide that up. So I'm going to use 3 as my only potential point of inflection, or the only potential place where I might change concavity. So those are your intervals. We are now going to take a test value. 0 is a pretty nice value from this interval. Anything in this interval, 100, 90, whatever, anything bigger than 3. We are taking these values and we are not filling them into the function. We are not filling them into the derivative. We are filling them into the second derivative. I like the factored form just because it's convenient. So taking 0 and filling it into the second derivative. 6 times 0 minus 3 is a negative. That's positive times negative. Second derivative is negative. Taking 100, filling it into the derivative. 100 minus 3 is clearly positive. That's a positive value. So, here's what we have now. The second derivative has changed sign. The second derivative, 2 derivatives away, will tell us that the original function is concave downward because the second derivative is negative. F is concave downward. Because the second derivative is positive on this interval, that makes F concave upward. So we have a point of inflection when x is 3. We do need to state clearly what we have and what on this paper is justifying that statement. So here we go. Conclusion statements. F has a point of inflection at, now here's the kicker. We know the x coordinate only. We have an x coordinate, and when I look back at the original directions, it does not say find the x coordinates of the point of inflection. It says find the points of inflection. So I need a corresponding y coordinate for this x value of 3. So we have to take our value of 3 and plug it back in. Plug it back into what? If I plug 3 into the second derivative, I get information about concavity. If I plug 3 into the first derivative, I get information about where f is increasing or decreasing. I don't want any of that. I just want a plain old y coordinate. So I need to fill f back into the original function. So, side of my paper here, I'm going to take 3 and fill it into the function itself, into f of x. 27 times 3. All right, so I've got 27 minus 81 plus 81. You're welcome. The answer to the y value is just 27. So I have f has a point of inflection at the full point, an x and a y coordinate, 327. Why? Because, and here's our justification, the sign change in the second derivative is going to be our justification. F double prime was negative on the interval less than 3, and the second derivative is now positive on x greater than 3. The sign change of the second derivative at the value of 3 is the justification. We can see that from the table, but we want to make it clear to anyone grading it, that's the important part that we use to justify. There you have it. Corn children, children of the corn, points of inflection for a function.